Assalamu alaikum, dear students. I welcome you all in the week 5 lectures of internal combustion engines, ME215. In today's lecture, I am going to cover chapter number 6 of book Denison, the textbook, and the name and the title of the chapter number 6 is Fuels. So these are the learning outcomes of today's lecture. So first of all, we will study that why it is important to study different types of fuels and their characteristics. That why it is important to study fuels. Then we will learn types of fuels, chemical structure of petroleum based fuels, important qualities of SI engine fuels, important qualities of CI engine fuels. Then in the later part of today's lecture, we will be studying the rating of SI engine fuels and rating of CI engine fuels, and at last we will study the calorific value of fuel. We will also study the high calorific value and low calorific value. So these are the learning outcomes of today's lecture. So student, let's discuss a little bit that why it is important to study different types of fuels. So uh, the fuels are being studied since the internal combustion engine came into existence. So we are studying the different types of fuels from the existence of internal combustion engines, and you know that internal combustion engines are heat engines, and heat engines convert heat energy into mechanical energy. And from where this heat energy comes, this heat energy comes from by burning fuel. We have fuel has the chemical energy, then we mix fuel, we burn the fuel in the presence of oxygen, then this chemical energy is converted into heat energy, and then this heat energy is converted into the mechanical energy. And since the heat energy is the main input of the heat engines, and heat energy is derived from fuel, so it is very important to study the fundamental knowledge of different types of fuels and their characteristics in order to understand the combustion phenomena in internal combustion engines. The characteristics of fuel also decide the design, efficiency, output, and reliability and durability of an engine. So, if these parameters, because these all parameters depend on the type of the fuel used. So you know that the gasoline engines are different from the diesel engine. So we are using a different fuel, and because of the different fuel, we have a different design, different output, efficiency, reliability, and durability of an engine. Uh, the other main reason of studying different types of fuel is that the choice of the fuel also if also play an important role in affecting the atmosphere, because you know that if we use a dirty fuel, then the emissions coming out of an internal combustion engine will affect the atmosphere, and if we use a clean or an expensive fuel, then it will less pollute the environment. So like for example, if you know that diesel engine is a dirty and a cheaper fuel, but its emissions are higher. So you remember, like we have the old buses like 4K and 4M, and like the big buses, they were using the diesel as a fuel, and these buses used to emit like dark soot and the other emissions. And then on the other hand, we have the CNG based cars, and the CNG based cars emit very less emissions. So the choice of the fuel also play a vital role in affecting the atmospheric pollution. So these are the main parameters on the basis of which we have to study the different types of fuel. So because of this, we have a separate chapter in the book Garrison on fuels. So fuels can be broadly classified into three categories. One is solid fuels, liquid fuels, and gaseous fuels. So one by one, we will study different advantages and disadvantages of solid, liquid, and gaseous fuels. So let's first study the solid fuels. So you know that in solid fuels we do not have many options. In solid fuel we normally have the coal, and you know that if you remember, like you must have seen in different videos and different old videos that in past we have steam engines, and in steam engines we used to use coal or powdered coal in the steam engines. Like you remember, there used to be a furnace on the steam engines, and there was a big pile of coal, and there were three or two workers who used to like throw the coal with the help of shovels in the furnace, and in the furnace the coal burns and the heat is liberated, and that heat is used to drive the steam engines. So these engines were used in the past or in the initial stages. Now these engines have become obsolete because of their handling problem. Like you know that because if we have solid fuel, then fuel will have a larger volume, like it will occupy a larger space in the vehicle, and we have to like dedicate a big portion of the vehicle to store solid fuel. So we have the handling problem, and then we have the solid residuals and ash formation. Like you remember, you know that we when we burn coal, we have the ash formation and the solid residual formation, and these ash and solid residuals greatly affect the environment. Like it pollute the atmosphere. In China in past have greatly used the coal based power plants now, and it very badly affected their atmosphere. Now their atmosphere have become so much polluted that they have shut down, or they are planning to shut down all the coal-based power plants. So that is why like the solid fuels were used in the past. Now they are not being used currently. Also, like we are thinking that we can convert the solid based fuels in the gaseous and liquid fuels, and then we can use the that solid or that liquid or gaseous fuel. Like you, with the help of like a fluidized bed converter, we can convert the coal into coal gas, and that coal gas can be used uh, to run the vehicles. But of course this process is very complicated, and like we need to have special devices. So the price of that fuel, like the coal gas, would be higher than the petroleum based fuels. So these points are mentioned in the slide, like because feeding is quite cumbersome. That is why the fuels in solid form have become unsuitable to be used in the IC engines. Like if you remember, like if I tell you that you have to use the uh, coal in your bike, then you must have a big like a big bag of coal, and there must be like a separate person who must be sitting at your back. Then he is then with the help of a small shovel, he must be throwing like that coal into the furnace in the bike, and the coal will burn, and then heat will be liberated, and the bike will move. So you can think about that how complicated will be the bike. Like you have to carry additional weight, additional person, additional equipment, and the size and the design of the engine will become very complicated. So the solid fuels are not being used in the internal combustion engines. Then the liquid fuels in most of the modern internal combustion engines, liquid fuels and mostly the derivatives of liquid petroleum based fuels are being used. For example, benzyl, alcohol, gasoline, and petroleum based products. However, petroleum products forms the main fuels for IC engine as on today. Like currently mostly petroleum based liquid fuels are being used, like petrol or diesel in the internal combustion engine, and kerosene in the aircrafts. Then we have the gaseous fuels. Gaseous fuels are ideal, like because gaseous fuels are in the gaseous form, and you know that if we need to burn fuel, we need oxygen, and oxygen is also in the gaseous form. So gaseous fuel, oxygen will mix very easily. That they can make a homogeneous air fuel mixture, and that homogeneous air fuel mixture can be burned very easily. So like the problem with the liquid fuel is that we can only use those liquid fuels which are volatile. That it means that fuel should be evaporated. That is that fuel should be converted into the vapor forms, into the vapor form, and that in and that vapor uh, molecules of the fuel will mix with air, and then a proper homogeneous air fuel mixture will be formed. So there is a problem with the liquid fuel, is that the liquid fuel should be volatile. So like for example petrol, you know that petrol is a highly volatile fuel. So if you take the petrol in a glass and you keep it and you put it open to the atmosphere, after some time you will see that all the petrol will be vanished, all the glass will be emptied. Like where this petrol will go, actually the petrol will evaporate. The petrol is highly volatile, so petrol will evaporate and it will convert into vapors and mix into the atmospheric air. But the gaseous fuels are ideal in the sense that the gaseous fuels are already in the gaseous form, and oxygen is also in the gaseous form. So so in this way gaseous fuel and oxygen can mix together and can form a homogeneous mixture very easily, and that fuel can be provided to the engine and the distribution system, and the starting of the engine can be eliminated. However, you know that the gas occupies a larger volume. So again, we will be facing the storage and handling problems. Like those who are using the CNG based cars, they must be experiencing these problems. That there's a if you want to run your car on natural gas, we will be using we will be using a very large cylinder at the back of the car, and that cylinder has weight and has very high weight. So the performance of the engine is affected by the presence of this CNG cylinder. Like you cannot put the dicky of the car will be occupied. You cannot put your luggage at the back of the car. Secondly, if the car is empty, the car is not empty actually, because the CNG cylinder is there, its weight is there. So like for example, you're always carrying one person in the form of CNG cylinder. So we face these storage and handling problem. That is why we use the compressed natural gas. Like you take the natural gas which is in the gaseous form, but you compress it. By compressing it, it will be converted into liquid form, and then you can store it very you can store it a little bit easier form. But then you will need a converter. That converter will convert the highly pressurized compressed natural gas into which is in the liquid form. Then it will be evaporated. There will be a special device called converter. The converter will convert into the low pressure natural gas, which will be in the gaseous form, and that gaseous form natural gas will be mixed with air, and the homogeneous air mixture is formed, and then the vehicle can be run. So similarly, we have the LPG, liquefied petroleum gas. Petroleum gas can be liquefied under high pressure, and its volume will be reduced, and it can be stored, and then it can be used in the vehicles, in the internal combustion engine. But then again, the setup will be expensive. Like you need to have um, because there will be a additional cost related to the uh, for the compression of the natural gas. If you go to the CNG station pumps, you will see that there will be a high compressors installed there, and the CNG station have a supply of natural gas from the Swiss Southern company, and that natural gas is compressed with the help of compressors, and then this compressed natural gas is feed it into the cars and the buses, etc. And for example, natural gas per kg price is like, let's suppose, 80 rupees. Then additional 20 rupees will be associated with the compression of the gas. Like you need big compressor, you need electricity to run the compressors. So the CNG cost will become will be increased. Okay, so now it was like a quick comparison of solid, liquid, and gaseous fuels. Now we will broadly discuss the chemical structure of petroleum-based fuels. Normally, like in the petroleum-based fuels, we have paraffins, olefins, naphthalene, and aromatics. What are what are paraffins? Actually, you have studied this thing in the second year chemistry, in organic chemistry. Paraffins are like alkanes. Its general formula is CnH2n plus 2. If like let's suppose n is 2, C2, 2 to the 4 plus 2, 6, CnH6, it will be ethane. These alkanes are uh, chain type compounds, and they are saturated because they have single bond, and the single bond is relatively stronger than the unsaturated bond, that is the double bond, or a pi bond. That is why they are called saturated, and because of the single bond they are stable. Olefins are also called alkenes. Alkenes have at least one double bond in their structural formula, and its general formula is CnH2n. They are also chain type compounds, and because of the presence of single bond, these compounds are unsaturated and these compounds are unstable. You must know that you must remember that these compounds are highly involved in different types of reactions. That is why, because they are unstable and they react with other elements. uh, Naphthenes or cycloparaffins are have the same general formula of like the olefins. So actually you can call naphthene is isomer of olefin, because the compounds which have same general formula but different structural formula, they are called isomers. So the difference between olefin and naphthene is that naphthenes are ring based compounds, that like the double bond will be broken, and the and like the compound will be the reaction will be such that the compound will be converted from chain based compound to the ring based compound, and because of the ring formation, its structure will become compact, it will become saturated, and it will become stable. Then we have aromatics like the benzene, and like the most popular compound of aromatics family is like benzene, C6H6. They are ring compounds, and they are highly unsaturated, and they are most unstable because of the presence of the moving double bond. So these things you have learned very detail in the second year chemistry. So I'm not going to much detail of these compounds. So it was a brief introduction of petroleum based fuels. So in for SI engine, like we need a fuel with best anti-knock characteristics. Like we will prefer a fuel with best anti-knock characteristics, like because you know that in SI engine fuels, in SI engines we compress air fuel mixture. Like we have a carburetor where air and fuel are mixed, and that air fuel mixture is supplied to the cylinder. It is compressed in the compression stroke, then we give a spark with the help of a spark plug, and then this air fuel mixture is readily combusted. It will be converted into, it will be very rapidly converted from air fuel mixture to the exhaust gases. And and we are compressing the air fuel mixture, it is possible that because when we compress a gaseous mixture, its temperature increases. So this is a normal observation, no? That when we compress something, its temperature increases because of the compression, that the molecules come close to each other, and because of this thing, the temperature of the gas will increase. So when you are compressing the air fuel mixture, it might be possible that the air fuel mixture reaches to the self ignition temperature of the fuel, and when the mixture reaches to this temperature, combustion will be started. The uncontrolled abnormal combustion will be started before the spark plug giving the spark. So this is called knocking. This is the abnormal combustion. It will disturb the order of combustion in the engine. It will produce noise, it will produce audible sound, it will produce vibration, and it will greatly affect the performance of the SI engine. So SI engine, the biggest big draw the drawback of the SI engines is that we cannot use high compression ratios in the SI engines, because if we use the high compression ratios, the air fuel mixture will reach to the self ignition temperature of the fuel, and the abnormal combustion will take place and knocking will take place. So in order to avoid this problem, we need a fuel with best resistance to knocking. Anti-knock characteristic means resistance to best resistance to knocking. So we need fuels which can resist knocking, that they should avoid the phenomena of knocking. So anti-knock quality is that is resistance to knocking is proportional to number of carbon atoms and compactness of the molecular structure. If the molecule, if the fuel molecular structure is compact, it means its resistance to knocking will be higher. If the fuel molecular structure is compact, then it means that its self ignition temperature will be high. Or if the number of carbon atoms are higher in the fuel molecule, then it's obviously then its boiling temperature or the self ignition temperature will be higher, and higher the self ignition temperature means that higher the resistance to knocking. So we can compress it to high values of compression ratio. So if we increase the number of carbon atoms, or if we increase the compactness of molecular structure of fuel, then it means that we can increase the anti-knock quality of the fuel. That is, resistance to knocking can be increased. So paraffins are not best fuel. Uh, Poorest anti-knock qualities. Like paraffins have poorest resistance to knocking, especially like methane, ethane, like the initial compounds where the carbon atoms are less. So their resistance to knocking will be very poor. As the number of carbon atoms is increased, like if you go towards like octane, nonane, hectane, then their resistance to knocking will be increased. But like the initial compounds of paraffin family like methane, ethane are not suitable for SI engine fuels. Aromatics are best fuel. Like it has been observed that aromatics based fuels have best resistance to knocking. Like they can, when they are used in the internal combustion engine, they can be operated at higher values of compression ratio. So aromatics are preferred uh, for SI engines. So we need a fuel which have higher percentage of concentration of aromatics in it, and the paraffin's concentration should be low. For as compared to the SI engine fuel, for CI engines we need a fuel with certain volatility. And now I should remind you that what is the difference between CI engine and SI engine. The difference is that in CI engines we compress only air. We compress only air, and then when we compress the air and the piston reaches to the top dead center, we spray the fuel into the compressed air, which temperature is above the self ignition temperature of the fuel, and the fuel starts combusting when it is sprayed into the cylinder. So like in SI engines, fuel first should evaporate, so its volatility should be very high. And when the air fuel mixture is prepared, and then this air fuel mixture is supplied to the cylinder, whereas in CI engines only air is compressed and then fuel is sprayed. So like we need a moderate values of volatility is like the evaporation ability of the fuel. If volatility is high, it means that fuel will readily evaporate. It will quickly evaporate, and it will be converted from liquid phase to the gaseous phase. So like we need moderate values of volatility, but for CI engines, but for SI engines we need a fuel which should be highly volatile. But for CI engines we need a fuel whose volatility should be moderate. Now, number of atoms, the boiling temperature is proportional to number of atoms. Higher the number of atoms, higher will be the boiling point. Like it makes sense. If you have a compound, like if you compare octane with methane, like octane has higher number of carbon atoms, higher number of hydrogen atoms, so like it's a heavy compound, so its boiling temperature will be higher. And the heavier the molecule, it will be its volatility, its evaporation ability will be lower. So like if the compound is lighter, then its chances of evaporation is will be higher. So lighter molecules will evaporate very easily. So as the number of atoms are increased, volatility will decrease. Paraffins are best fuel for CI engines, and aromatics are not best fuel. Like we have seen that paraffins have low self ignition temperature, and aromatics have high self ignition temperature. So in CI engines we need a fuel whose self ignition temperature should be low, so that as soon as fuel is sprayed into the compressed air, its combustion should be started. So we need a fuel whose self ignition temperature should be low. That is why paraffins are preferred in CI engines. But paraffins are not preferred in the SI engines because their self-ignition temperature is low. Then the heating value generally increases as the proportion of hydrogen atoms to carbon atoms in the molecule increases. What is the reason? The reason is that the heating value of hydrogen is higher than the heating value of carbon atom. So higher the hydrogen atom, the higher will be the heating value of that fuel. And paraffins have the highest heating value, and the aromatics have the least heating value, because if you can see that in paraffins we have H2N plus 2, 2N plus 2, and we have and we have in aromatics we have 2N minus 6. So like if we have 6, N is 6. So 2 6 are 12, 12 plus 2, 14 hydrogen atoms will be there in C6 H14. Whereas if we go for aromatics, then C6, 2 6 are 12, 12 minus 6, 6. So there will be only 6 hydrogen atoms. So these number of hydrogen atoms are lesser than the paraffin. So paraffins heating value should be higher than the aromatics because of the higher number of hydrogen atoms. Okay, so now we will study some important qualities of SI engine fuels. The first of all, the very important property of SI engine fuel, as I already explained, is volatility. The SI engine fuel should be highly volatile, because we need such fuel which should be very quickly converted into gaseous form, and then this gaseous form of fuel will be mixed with air, and homogeneous air fuel mixture will be formed, and then this air fuel mixture will be supplied to the combustion chamber through the intake manifold. So volatility should be high. So what is volatility? Volatility is like evaporation of liquid at the certain temperature. So if fuel is not converting into gaseous form, then it means that its volatility is very low. And if the fuel is very quickly converting into gaseous form, then it means that its volatility is very high. So in this graph, temperatures and volume of fuel evaporated are plotted. So you can see that on y-axis we have temperature, and on x-axis we have volume of fuel evaporated. So 0% fuel evaporated, 20% fuel evaporated, 40%, 60%, 80%, and 100% fuel evaporated. And this percentage of volume evaporated depends on temperature. So as you can see that, let's suppose this is the starting temperature, like something like 38 degrees Celsius something. And as you can see that as the temperature is increasing, the volume of fuel evaporated is increasing. So it makes sense because if you increase the temperature, the volatility, the evaporation characteristics, the evaporation rate of the fuel will be increased. So at room temperature, uh, the fuel evaporated is 0%. As we increase the temperature slightly, 1%, 2%, 5%, and 10% fuel is evaporated. So this is called uh, uh, a volatility graph of the fuel, and it should be like this. It should not be like in this form, that if it is like this, then this fuel is not suitable. Because what is happening, this graph is showing that as the temperature is increasing, as the temperature is increasing, the volume of fuel evaporated is decreasing. So this is not desirable trend, because as the temperature increases, the volume of fuel evaporated should be increased. It should not be a decreasing trend. It should always be like an increasing trend. And there are two graphs. One graph is for winter. Winter is for like the solid line, and summer is like the dotted line, and the dotted line is above the solid line. So it makes sense, because in summer we have higher atmospheric temperatures, so the fuel will evaporate more in summer as compared to winter. So this thing, you like those who have cars or bikes at their home, they must have experienced that in 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 winter season, at sometimes in morning, it you face problems to start the vehicle, like bikes or cars. They feel you face problem to start the engine. It is because of this. It is because of the fact that because of the low temperatures in winter, the fuel volatility is decreased, and the air fuel mixture is not formed, and the engine is not started. So you face these problems. So in order to cover these problems, like we use the glow pump, which heats the fuel and avoids the problem of starting problems in internal combustion engine. The second characteristic which is required in the SI engine fuel is that they should support the starting and warm up. Like you can see that this is at room temperature, at least like 5 to 10%. At 5 to 10% of the fuel should be evaporated. If we have this characteristic, like at room temperature about 5 to 10% of the fuel is evaporating, then it is good. So we need this characteristic in the SI engine fuel. So if we have this characteristic, then we will not face the startup and warm up problems. uh, and and for this we need the low distillation temperatures are desirable throughout the range of distillation curve for best warm up. So like this is the distillation curve, and in the distillation curve, low distillation temperatures are required. So if for example 5% or 10% of the fuel is evaporating at like 100 degrees Celsius, then this is not good. This is not a good fuel. So uh, uh, the temperatures at which about 5 to 10% of the fuel is evaporated should be low, like it should be close to the room temperature. Okay, so like the fuel characteristic should be such that it should avoid the problem of starting and warm up, but it should also have such characteristic that it should support the whole operating range of the engine. Uh, like we have seen that at room temperature, like 5 to 10% of the fuel should be evaporated, but as the temperature is increased, the percentage of the fuel evaporated should be increased, so that engine can be operated throughout the entire operating range of the engine. So this is required for the better acceleration characteristics of the engine. And if we have such characteristic that the fuel volatility is increased with the increase of temperature, then liquid droplets are not formed in the intake manifold, because if the fuel is not evaporating, then the liquid droplets are formed, na? But if the fuel volatility is high and it is supporting the whole operating range of the temperature, then then the fuel will readily evaporate, and the liquid droplets will not be formed. Okay, so crankcase dilution. Now, let's suppose if the fuel is not evaporating, if the fuel is not volatile, then what will happen? Fuel in the liquid form will go into the engine, and we have a layer of lubricating oil on the moving parts. Like let's suppose we have the crankcase, we use oil in on the crankcase. We have a layer of the lubricating oil, and when the fuel will go into the liquid form in the engine, then these liquid droplets will mix with the lubricating oil, and then they will remove the layer of lubricating oil from the crankcase, and the crankcase will become diluted. Like the lubricating oil will be removed from the crankcase, and then this crankcase will be exposed to the will be exposed, like the crankcase will be moving, that part of the crankcase will be moving without lubricating oil, so it will affect its life, it will affect it will deteriorate the shape of the crankcase. And secondly, when the liquid fuel go into the into the engine, it will mix with lubricating oil, and the lubricating oil performance will be affected, like it will not remain oil, like it will start becoming it will from the oil, like you know that the oil has a very sticky touch, like it has like a sticking property, and like it's different from the liquid. So when the fuel is keep on mixing with the lubricating oil, so its oilness will be lost, and ultimately the lubricating oil will be deteriorated, and once the lubricating oil is deteriorated, the engine will start getting heat up. There will be like the frictional heat losses, the cooling performance will be affected, the engine will be affected, and ultimately the engine will become seized, like the moving parts will expand so much that the engine will get seized, and it's because of the low evaporation characteristics of fuel. So a fuel should be such that the SI engine fuel should be such that it should be highly volatile, so that liquid the fuel should not go into the liquid form into the engine. Okay, now number five characteristic is slightly different from the above four properties. Like we have studied that the SI engine fuel should be volatile, but if the SI engine fuel is very volatile, then what will happen? Uh, too much vapors of the fuel will be formed, and too much vapors of the fuel are also not desirable. So because we know that the like the passages are very thin, like the carburetor lines and the line through which the air fuel mixture flow, these lines are of very small diameter, and when very high vapors of the fuels are being formed, then what will happen, these vapors will block these small diameters passages, and the air fuel mixture will not flow. So this thing you have seen that one sometimes, like you have pipes, the water pipes at your home, and sometimes in when you have the geyser is working, then even the small water reservoir is full at the roof, still you do not get water at the in the taps. So what happens, some air bubbles are trapped in the water lines, and these water bubbles block the flow of water in the lines. So the same thing happens in the engine passages, that if too much vapors are being formed of fuel, then these fuel vapors will block the flow of air fuel mixture. So this characteristic requires that the fuel boiling temperature should be high, and it is contrary to the other four properties, like property number 1, property number 2, property number 3, and property number 4 have demanded that the fuel volatility should be high. That is, the fuel boiling temperature should be low. But this property requires that the fuel boiling temperature should be high. So, like, we have to make a compromise, that fuel volatility should be moderate. It should not be very high. It should not be very low. Because if the fuel volatility is low, then we will face the crankcase dilution. We will face the operating range performance. We will face the starting and warm up problems. And if the fuel volatility is very high, then we will face the problem of vapor lock characteristics. So in order to avoid all these problems, we can use a fuel with a certain suitable value of the volatility. Number six, the anti-knock quality, like this is the obvious requirement that we need such SI engine fuel which should have a good anti-knock quality. That is that is a fuel should have a good resistance to knocking. Number six, uh, desired characteristic of SI engine fuel is that they should not form the gum deposits. So you must have seen that actually that the gasoline and the petrol, they are the petroleum based fuels, and they are hydrocarbons. So the problem with the hydrocarbon is that when you store them in a tank, then and when they react with oxygen, like the white gummy compounds are formed, and solid gummy substances are formed at the layer which is exposed to the atmosphere. um, and then like if you do not use your vehicle and like put it and the fuel is there in the fuel tank for like 2 months, 3 months, or 6 months, then these gums are formed in the solid tank. And then when these solid gummy substances go into the engine, they will damage the internal combustion engine. So the desired quality of the SI engine fuel is that they should not form the gum deposits. The amount of gum increases with increased concentration of oxygen, with rise in temperature, with exposure to sunlight, and also on contact with metal. Like if the fuel is exposed to sunlight, then these gummy substances are formed. And if we increase the concentration of oxygen, then then the concentration of gummy substances will be increased. So gasoline with high gum content will cause operating difficulties such as sticking valves, piston rings, carbon deposits. Like if we have the gummy substances, then the carbon will start depositing on the piston rings. Gum deposits in manifold, clogging of carburetor jets, and enlarging of the valve, stems, cylinder, and piston. Like if the gum is being deposited on the cylinders and piston, then ultimately the piston diameter and the cylinder size, the piston diameter will start increasing, the cylinder size, the cylinder internal diameter will start decreasing. So this thing will happen. So we need such SI engine fuel which should limit both the gum content of the fuel, and it has tendency to form gum during the storage. And the seven characteristic of the SI engine fuel is that it should have a very low content of sulfur, because if the sulfur content is high in the fuel, then sulfur is a corrosive element, and it can corrode the fuel lines, carburetors, injection pumps, and it will also unite with oxygen to form sulfur dioxide. And the sulfur dioxide is a highly toxic uh, gas, and in the presence of water at low temperature they form sulfuric acid, and sulfuric acid is like it's a very dangerous acid. So we need such fuel for SI engine that should have a low sulfur content. So these were the some important characteristics of SI engine fuels. Now we will study the important qualities of CI engine fuels. So the first quality is knock characteristics. So now you must be wondering that we have studied that knocking problem only occurs in the SI engine, but the knocking also occurs in compression ignition engines. But the reason of knocking in CI engine is very different. So what I'm saying that knocking occurs in both types of engines, like in SI engines and in CI engines. Knocking occurs in spark ignition engines as well as in compression ignition engines. But the reason of knocking in SI engines and CI engines is totally different. So what is the reason of knocking in CI engines? That when knocking will occur in CI engine. So I will explain. So as I have told you many times that in compression ignition engines we only compress air, and then we spray the air. Then we spray the fuel into the compressed air. So now what happens? Let's suppose let's suppose that because of some reasons, fuel is not burned as when it is when it is sprayed into the compressed air. What will happen? Let's suppose the piston is uh, at top dead center, air is compressed, air is hot, and you have sprayed fuel into the compressed air. First droplet of the fuel will come into the cylinder, and let's suppose that because of some reason this fuel is not burned. second droplet of the fuel will come, it is not burned. Third droplet of the fuel will come into the cylinder, and it's not burned. So now what will happen, that fuel will start accumulating into the cylinder, and when the combustion starts, this accumulated fuel will burn in an abnormal way. So like, if first droplet is burned, second droplet is when the fuel first droplet is come the first droplet comes into the cylinder, it is burned. Second droplet comes into the cylinder, it is burned. It is a normal combustion. But if the fuel is not burning, but it is accumulating into the cylinder, and when its combustion takes place, then it's a abnormal combustion. It will take its combustion will not take place, actually its detonation will take place, and it will, again, it will produce the audible sound, it will produce the disturbance in the engine, it will produce vibration in the engine, and it will be act like it will produce the same sound like in as produced in the knocking. So knocking will take place. So in a spark ignition engine, what happens, if you compress the air fuel mixture, and if you compress the air fuel mixture so much that the air fuel mixture reaches to the self ignition temperature of the fuel, then the air fuel mixture will be combusted before the spark plug giving the spark. So this is the reason in the reason of knocking in spark ignition engine. But the reason of knocking in compression ignition engine is that when you have compressed air, and the piston has reached to the top dead center, and you have started spraying the fuel. Ideally what should happen, that as the first droplet of the fuel comes into the cylinder, it should be combusted immediately. It should be combusted immediately. And when the second droplet of the fuel comes into the cylinder, it should be combusted immediately. And when this is happening, this is normal combustion, and no audible sound will be produced. But let's suppose that because of some reasons, let's suppose that fuel have a high self ignition temperature, and you have sprayed such fuel into the compressed air. First droplet comes, second droplet comes, third droplet comes, but combustion is not started. And then this fuel will start accumulating into the cylinder. And when the actual combustion starts, this accumulated fuel will be burned in an abnormal way. Its detonation will takes place, and it will produce the audible sound in the CI engines. So we need such fuel, that this is called ignition lag. That when the fuel is sprayed and it's not combusting, this is called ignition lag. And ignition lag will be higher when the ignition lag will increase with the increase of self ignition temperature of the fuel. If you use a fuel with high self ignition temperature, then its ignition lag will be higher. And if you use a fuel with a very low self ignition temperature, then its ignition lag will be very, very low. So we need such a fuel in for the CI engines whose self ignition temperature is very low. Then we can avoid the knocking in CI engines. So uh, we need such fuel. uh, in general, the best fuel will have a cetane rating, uh, will have a high cetane rating. That is, it means a short ignition lag. We will study the octane number and cetane number in the later part of this lecture. The second property of the fuel which is required for the CI engine fuel is the volatility, but it should not be. But we need fuel which should be moderately volatile. They should not be highly volatile. The starting characteristic, like, it is very easy to understand that we need a fuel. We need such a fuel in the CI engines that should provide very good starting characteristics of the engine. Like, it should be the this requirement demands that high enough volatile to form a combustible mixture readily, and high cetane rating in order that the self ignition temperature is low. uh, like, fuel should be volatile enough that the a proper combustible air fuel mixture is formed, and and fuel is combusted. Because if the fuel is not evaporating, then uh, the self ignition temperature of the fuel will become high, and the combustion will not take place. And but if the fuel is enough volatile, then a good homogeneous air fuel mixture is formed when you spray the fuel into the hot air. Like you when you spray the when you spray the fuel into the hot air, what happens, it absorbs heat from the compressed air, and it starts evaporating, and gaseous fuel is formed, and then this gaseous fuel will be mixed with hot air, and homogeneous air fuel mixture is formed, and then it will be combusted. So if the homogeneous air fuel mixture is being formed, it means that its self ignition temperature will be low and it will be very easily combusted. Now, fourth property of the desired property of the fuel of the CI engine fuel is that they should not form the smoking and odor when they are burned in the engines. Normally, we use cheaper fuels in the CI engines, and these cheaper fuels have higher values of viscosity, but they should not have too much viscosity that that the fuel is not getting able to flow into the fuel lines or in the other passages. So we need such a fuel that it should have such viscosity that fuel can easily flow through the different passages of the engine. The fuel should not corrode and wear the different parts of engine. This is the sixth requirement of the CI engine fuels. It should be easily handled. Its properties should be such that it can be easily handled. It can be easily stored. It can be easily supplied to the different parts of the engine. So it should have such characteristics. Okay, now we have studied different important qualities of SI and CI engine fuels. Now we will start a new topic, rating of SI engine fuel. Actually, rating of SI engine fuel is the resistance to knocking. So if we have if I say that the rating of SI engine fuel is, let's suppose we have two fuels, and we can say, if I say that let's suppose we have fuel A and fuel B, and I say that fuel A has high fuel rating and fuel B has low fuel rating. It means that fuel A has high resistance to knocking and fuel B has low resistance to knocking. So rating is like a number from 0 to 100, which describes the resistance to knocking. So like we can, like we want to develop a method according to which we can rate different SI engine fuels. So like if we have a fuel with 100 number, we can say that its rating is maximum, and its resistance to knocking is maximum, and that fuel can be used at at high values of compression ratio, and high values of compression ratio means higher efficiency. And if we have like 0 or 1 rating of SI engine fuel, then it means that it has a very poor rating. It's very poor fuel, and its resistance to knocking is very poor, and this number is actually octane number. So octane number defines the anti-knock value of the SI engine fuel. So we know that SI engine fuels differ widely in their ability to resist knocking depending on their chemical composition. Uh, so the resistance to knocking depends on chemical composition, and the some other parameters also affect the resistance to knocking, such as fuel air ratio, ignition timing, dilution, engine speed, shape of the combustion chamber, ambient condition, compression ratio, engine cooling, etc. These all parameters also affect the resistance to uh, knocking, and we want to develop a satisfactory rating method for comparing the anti-knock qualities of the various fuels that has been established. Look, like we have established a satisfactory rating method for different fuels. Uh, in order to determine the anti-knock resistance characteristics of the fuel, the engine and its operating variable must be fixed at standard values. So like when like we have like when if we want to determine the octane number or rating of two fuels, then these two fuels should be tested in in the same engine, and at the same operating variables. So the engine and the operating variable must be fixed if you want to compare two fuels. So this is the requirement of the method which we will be using to determine the octane number. So what is the main idea of this method, the main idea of this method is that the knock rating of an SI engine fuel is found by comparing fuel with primary reference fuels under prescribed conditions. So if you remember in chemistry, when you want to determine the um, molecular weight of an element, then you develop some standard, like, and that standard is carbon atom. So if you want to find the molecular weight, then you always compare the molecular weight of the element with the molecular weight of the carbon atom, because the weight of the carbon atom is standard. So we will do the same thing, that we will first select the reference fuels, the standard fuels, and these reference fuels uh, are isooctane and normal heptane. So isooctane has very good anti-knock characteristics, that it has the highest resistance to knocking. When it is used in different engines, it is observed that isooctane has highest resistance to knocking. So we have arbitrarily assigned a rating of 100 octane number to isooctane. Then we have other standard normal heptane, and we have observed that normal heptane has very poor anti-knock quality. That is, if we use normal heptane, and then at very low values of compression ratio, we start observing the knocking. So it means that normal heptane has very poor resistance to knocking. And when we use isooctane in an engine, we can run the engine at very high values of compression ratio, and we do not observe the knocking. It shows that it has very high resistance to knocking. So we arbitrarily assign 100 octane number to isooctane, and we arbitrarily assign 0 octane number to normal heptane. So now we have two standard. Isooctane has 100 number, and normal heptane has 0 number. So let's suppose uh, let's suppose we want to determine the octane number of fuel A. So what we will do, we will take fuel A. Let's suppose we have fuel A. We will take fuel A, and we will put into an engine, and at some standard operating conditions, we will we will use this fuel at different values of compression ratio. Let's suppose we will use the fuel at compression ratio 1, compression ratio 2, compression ratio 3, compression ratio 4, until we start observing the knocking. That what we are doing, we are using fuel A into the engine, and we are increasing the values of compression ratio, and we stop increasing the compression ratio until we observe the knocking. When we observe the knocking, we will note this value. Now we will remove fuel A from the engine, and we will try to prepare a mixture from isooctane and normal heptane, and we will take different proportion, like 10% isooctane, 90% normal heptane, 20% oxyoctane, 80% normal heptane. Like, we use different percentages of isooctane and normal heptane, and we will try to uh, get the knocking at the same value of compression ratio at which we observe the knocking for the case of fuel A. When we reach to this composition, let's suppose we get the knocking at the same values of compression ratio on this condition, that 80% is isooctane and 20% is heptane. So we can call that the octane number of this fuel is 80%, is 80. So I repeat, it's very simple. Let's suppose you have fuel A. You will put fuel A into the engine, and you will use some standard operating conditions, and then you start varying the compression ratio 1, 2, 3, 4, 5, 6. Let's suppose at compression ratio 9, we observe knocking for fuel A. So we note this value. Now we will remove fuel A from the engine, and we will put a new fuel into the engine into the same engine, and at the same operating condition. Now we will form this fuel mixture by mixing isooctane and normal heptane. Now we can use different proportions of isooctane and normal heptane. Let's suppose we can take 50% isooctane and 50% normal heptane, and there could be like different combinations. But like we, let's suppose we take 50% octane isooctane and 50% normal heptane, and we uh, check again that at what compression ratio the knocking is occurring. If the knocking is occurring, let's suppose at compression ratio value of 9, then it's okay. If it is not occurring at compression ratio 9, then we will again prepare the we will again prepare the mixture by mixing isooctane and normal heptane, and and the mixture which is giving the same value of compression ratio at which knocking is occurring, then we will note the proportion of the isooctane and normal heptane, and the proportion of isooctane will be the octane number of that fuel. So this is exactly defined in this definition. So if you read this definition, you will understand that the percentage by volume of isooctane in a mixture of isooctane and normal heptane which exactly matches the knocking intensity of the fuel in a standard engine under a set of standard operating conditions. So this is exactly this is exactly the same statement which I have tried to explain you in wording or in more detailed way. The percentage by volume of isooctane in a mixture of isooctane and normal heptane which exactly matches the knocking intensity of the fuel in standard engine under a set of standard operating conditions. So now the question is, can we have octane number greater than 100? So the answer is yes, we can have octane number greater than 100. How can we achieve octane number greater than 100? By adding different additives. Like we have different compounds like tetraethyl lead. If we add tetraethyl lead to the fuel, then the fuel octane number will actually become greater than 100. So but the problem is that tetraethyl lead is not good, because when you use the tetraethyl lead into the fuel, the lead particulates will be formed in the exhaust gases, and then these lead particulates will cause cancer problems in the living things. So there are some other additives are also available which can be added into the fuel, and then the octane number higher than the 100 can be achieved. And in the book, if you go to chapter number 6 of book Kennison, there is a formula given which relates the octane number uh, related to the percentage of tetraethyl lead. You can determine that what will be the octane number, like 102, 103 or 104, depending on the percentage of the tetraethyl lead added into the base fuel. So if the octane number high octane number shows that high resistance, and low octane number shows low resistance. So if you have a fuel with let's suppose if you go to the market and you have two fuels, one fuel has high octane number and one fuel has low octane number. So you should go for the high octane number fuel, because high octane number fuel will have greater performance. Because if you buy a high octane number fuel, then that fuel can be then that engine can be run to at higher values of compression ratio, and a higher compression ratio mean higher efficiency and higher performance. Similarly, the rating of SI engine fuels is determined in the same way, that we use the two standards, and the standards are different in the CI engines. One is normal cetane, which is arbitrarily assigned 100 cetane number, and alpha methyl naphthalene C11H10, which is assigned arbitrarily an cetane number of 0. So the rating of CI engine fuel is determined with the help of a cetane number. Like we have studied, the octane number defines the rating of SI engine fuel. So the cetane number defines the rating of CI engine fuel. So if we have high octane number, it means that this fuel have very low self ignition temperature, and this fuel has very low ignition lag, and that fuel, when it is sprayed into the cylinder, it will be immediately burned. if the cetane number is high. So we will do the same thing, that we will, let's suppose we will take a fuel A, and we will run the engine with fuel A, and we will observe that at what values of compression ratio the knocking is observed. Then we will remove fuel A from the engine, and we will make a fuel mixture by mixing normal cetane and alpha methyl naphthalene, and we will try to approach to the same value of the same intensity of the knocking. And when this is achieved, we will note how much percentage of normal cetane is present in that fuel, and that will be the cetane number of the fuel. So you can read this definition, you will understand. And the cetane number can be easily improved by adding like additives such as amyl nitrate, ethyl nitrate, or ether. If you add these compounds in the CI engine fuels, then the cetane number will be improved, and the cetane number improved means the performance of the engine will be improved. Now let's come to the last topic of today's lecture, the calorific value. What is calorific value? Calorific value is the thermal energy release per unit quantity of the fuel. Let's suppose 320 kilojoule per kilogram is the calorific value of a fuel. It means that if you burn 1 kilogram of fuel, then 320 kilojoule of energy will be released. So this is the meaning of calorific value. And there are two types of calorific value: high calorific value and low calorific value. High calorific value is when the fuel is burned completely and the products of combustion are cooled back to the initial temperature, then it will be high calorific value. So what is the logic? The logic is that you know that the products of combustion are CO2 and H2O, and and when combustion takes place, it's a highly exothermic process, so high amount of heats are released, and then this heat will be absorbed by H2O, and H2O will be in the form of gaseous form. So like some useful heat which is absorbed, which is released by burning fuel, that heat will be absorbed by water, and water will be evaporated, water will be boiled, and it will be converted from liquid phase to the gaseous phase. So and when the combustion products are cooled back to the initial temperature, then it means that the H2O will be again brought back to the liquid phase. The gaseous H2O will be condensed, and the amount of heat which is absorbed, it will be released, and then the heat which is released, that can be used uh, additionally. So the calorific value will become high, like we will have high amount of heat will be released. And when the products when the fuel is burned completely and the products of combustion are not cooled back, and the combustion products are thrown into the atmosphere, then that value will be low calorific value. And what is the logic? The logic is that when you are not cooling the products to the initial temperature, to the initial room temperature, then what is happening? The amount of heat which is absorbed by H2O, that cannot be recovered, and H2O in gaseous form will be dumped into the atmosphere. So I repeat again, um, there are two values of calorific value: high calorific value and low calorific value. So high calorific value is when the fuel is burned completely and the products of combustion are cooled back to the initial temperature, then it will be high calorific value. And what is the logic? Logic is that when you burn fuel, H2O will be formed, and that H2O will be converted from liquid to gaseous form by absorbing some heat which is released by burning fuel. So, and when the products of combustion are cooled back, these gaseous this H2O in the gaseous form will be condensed, and heat will be released, and that heat can be used by to run the engine, and the high amount of heat will be released, so it will be high calorific value. And when the fuel is burned completely and the products of combustion are thrown back to the atmosphere without cooling them back to the initial temperature, then that value will be low calorific value. And when the products of combustion are thrown to the atmosphere, then what is happening? The heat which is absorbed by H2O, that cannot be recovered. So the value will be low calorific value. Okay, so now these are some your task which you should do at home as a homework. Now you should search for the examples of solid, liquid, and gaseous fuels. Like for liquid, you can name like the petrol, diesel, kerosene. These are the examples of liquid fuels. Then for the solid fuel, then gaseous fuel, you should Google uh, different types of solid, liquid, and gaseous fuels. At least 10 each. Make a comparison between knocking of SI and CI engine. So I have explained in the in the lecture that the reason of knocking in SI and CI engines is completely different. So you should make a comparison that what is the comparison between the knocking of make a comparison between knocking of SI and CI engine. Study the petrol refining process. So this is present in the book Garrison, and this thing you have also done in the in the in the in the in the like in the metric or in the intermediate courses. That is why we have skipped this topic. And actually the basic idea behind the petroleum refining is that we take the crude oil and we heat it to a very high temperature, and then we start cooling it. And when we start cooling it, um, uh, like crude oil is a mixture of different fuels, and different fuels have different boiling temperatures. So when you start cooling it, the fuel which have like um, uh, high boiling temperature, then it will start condensing. And so the fuel will the fuel will have different boiling temperatures. So when you cool it, you will get uh, fuel will be condensed at different temperatures, and then you can remove the condensed fuel at the bottom of the chamber. So the details of the petrol refining process is given in the book. So I recommend you to go through to this topic. um, this is given on page number 190 of book Garrison. And then at the end of this topic, like different processes are also mentioned, like the cracking, hydrogenation, polymerization, isomerization, blending, reformation to increase to increase the performance of the petrol refining process. So this is your task. So you should prepare this topic. This topic may come into the exam, and you should not say that this is not covered in the lecture, because I have given you a homework, and this is your task, and you have to do it by yourself. Then make a cost per unit comparison of SI and CI engine fuel. Let's suppose gasoline is used for SI engines and diesel is used for CI engines. You should go to the market and ask the current prices of the petrol and the diesel and the other fuels. And you can also do it on online, like on the Google. You can search these values on the PSO or the Shell and the Parco sites. You can see the values, the current prices of the petrol, diesel, and the other fuels. You should also make a table, and in this table you should tabulate the values of volatility, ignition temperature, sulfur content, octane number of petrol. Let what is the exact number? Let in numbers. If I ask you in the exam, the volatility of petrol is this, you should remember the number like 5, 10, 30, 20. Ignition temperature 100, 2000, 2050 degrees Celsius. What is this ignition temperature of the fuel? Octane number, sulfur content. Similarly, you should make a table with the values of volatility, ignition temperature, sulfur content, cetane number of diesel. So this is the homework, and these questions may be asked in the quizzes or in the midterm or in the final exams. So with this, I end today's lecture. I hope you have achieved the learning outcomes of today's lecture. So the learning outcomes of today's lecture were that we need to study the important characteristics of SI engines and CI engine fuels, why it is important to study fuel. This thing we have studied different types of fuels. We have studied some general qualities of SI and CI engine fuel. Then we studied the octane number and cetane number, which are the rating of SI and CI engine fuels. And then we at the end of the lecture we studied the calorific value, high calorific value, and low calorific value. So see you next time. Allah Hafiz.